Welcome back, I guess. First thing is to kind of check where you come from here. Who's been to my Spring Framework 5 session earlier today, the JDK 8 and 9.1? Okay, well, it's actually more diverse than I thought it would be. Who's an active Spring Framework 5 user here? Who's already on Spring Framework 5? Who's on Spring Framework 4 for the 3? Yeah, okay, yeah. Well, I could have predicted that result. That's roughly where we are, right? Spring Framework 5 is GA, but it's of course only making its way into newly set up projects at this point. Anyway, so for the purposes of this session, I chose to take once more a different perspective. This is not a general Spring Framework 5 introduction by any means, quite on the contrary. This is well, I call it a hidden gem session. It's covering topics, certain favorites of mine, personal favorites of mine, refinements and like little features in Spring Framework 5 that we usually do not talk about so much and so clearly, right? So with Spring Framework 5, there's plenty of stuff that we are not talking about today, right? This is basically the executive summary that I'm usually showing. There's plenty of stuff from the functional API design, the reactive architectures, the Kotlin stuff, the reactor stuff, the whole baselining thing, and the JDK 9 topic, the Servlet 4, and all those things. This is basically what we usually cover. And it's mostly about the functional API design, Kotlin, reactive. That's what you usually will hear about when you go to a Spring Framework 5 session, or when you go to a Spring Boot 2 session and you get some of this stuff kind of shining through from Spring Framework 5 through Spring Boot 2 to you. So of course there's lots of benefits hiding in there. So these major themes are very intentionally major themes. But we always take the opportunity to bring a little refinements here or there into the framework. And the greatest examples, actually in the history of Spring, were probably 4.1, 4.2, and 4.3. I mean, in all fairness, those releases were really major releases. I mean, 4.1 was one of the richest feature releases we ever had. 4.2 and 4.3 were almost as rich. In other projects or other versioning schemes would have called them Spring Framework 5.0 and 6.0 and 7.0 probably, just in terms of the richness of the refinements. In Spring Framework 5, admittedly, doesn't actually have so many. I mean, if you're looking for many little refinements, check out 4.1, 4.2, and 4.3. They literally have hundreds of them. In Spring Framework 5, there wasn't so much left because keep in mind, and I've mentioned this earlier today, Spring Framework 4.3 was essentially a sort of early backport release of 5.0. So many of the things that you're already consuming in Spring Framework 4.3 were originally planned as 5.0 refinements. But due to the delays in the major themes, the reactive theme and the Kotlin theme, we decided to bring them into a Spring Framework 4.3 feature release. In other words, almost everything we could technically do in Spring Framework 4.3 on the Java 6 baseline and on the framework architecture in Spring Framework 4.3, almost everything we already brought to 4.3. So we really backported a ton of things. But there are still plenty of little nice refinements left that for one reason or the other only made it into 5.0. It's mostly technical reasons where we just couldn't really properly deliver them before. And I'm going to take you through a selection of like seven areas of refinement in the course of this session, right? All right. So everybody's favorite topic for a start, logging. And logging, of course, is like one of the most, well, it's one of the topics in Java that bugs me most because it's in the history of logging, right, from the early days of Log4j to Java util logging to then SLF4j and logback at the whole split from Log4j and then Log4j2 back at Apache and many side stories to it. It's really a quite convoluted history. And fortunately, things are in a little bit of a clearer shape, you know, that the picture is actually easier to grasp these days. Let's look at it from a 2017-2018 perspective. There aren't actually that many logging options that really matter. Log4j1 is end-of-lifed. Many of the old school logging frameworks supported in other Apache projects are end-of-lifed. So from an Apache perspective, there's Log4j2. That's the one thing everybody should be using from an Apache perspective. There's, of course, still SLF4j and logback. SLF4j is actually largely logback. Let's be frank, right? How many logging providers do you plug behind your SLF4j API these days? It's essentially, it's almost exclusively logback or a fallback to Java util logging. Oh, some people, of course, are using Log4j2 as a backend behind SLF4j. Quick check, who's an active Log4j2 user? Logback users? Right, yeah, all right. Other logging frameworks? Non-Log4j, non-logback? Java util logging on application server environments, maybe? It's, so this is roughly where we are. So it's actually quite a nice representation. Log4j2 is very actively developed. It's probably the most actively developed log framework today. There's Log4j 2.10 released very recently, so really very actively and very active feature refinements in Log4j2. That's great, right? Because a logback is a little dormant, I would argue. SLF4j is also a little not as actively developed as in previous years. So taking basically that position, those two logging frameworks that really matter, SLF4j as a common abstraction, and Java util logging as a fallback, in particular for application server environments with a common server-managed log sync. They usually use Java util logging as their front-end API. So those three really matter. That's what we need first-class support for. But where are we? Where were we? Where are we still with our framework code base? It was actually commons logging based. For the longest time, it was in the very early days Log4j 1.2 based, but everything that matters in Spring's history, it was commons logging based. And the commons logging API is actually shining through in quite a few places. It's not a totally internal dependency. We have quite a few places where log references or the whole commons logging mechanism shines through in the SPIs or in the base classes. Base classes with protected final logger references, like a log object, the commons logging log object as a final field that you can inherit from and use in subclasses. We have that in quite a few places, for better or for worse, right? Just because we internally had it like this, and because there are plenty of extensions out there, not necessarily application code, but really third-party extensions of SPIs, of common base classes of ours. They also talk to those inherited commons log fields, right? So that's exactly the situation that we were facing. A commons logging heritage that we have a hard time getting out of because binary compatibility for existing precompiled extensions. It's really hard to change the logging API for such a long-lived code base with so many extensions around us here. All right, so commons logging API heritage, 3 major logging targets, API targets, modern-day targets that we wanted to address. What's the solution? Well, we implemented our own commons logging bridge, and that's exactly what you get in Spring Framework 5 now. So state of the art, the Spring Core module in Spring Framework 5 declares a dependency on our bridge, which is Spring JCL, a separate module, part of the Spring Framework 5.0 umbrella. Spring JCL is essentially a logging bridge along the lines of the JCL over SLF4j bridge, so the commons logging bridge for SLF4j. It follows the same implementation pattern. So it's a direct implementation, doesn't follow the commons logging lookup rules. It auto-detects Log4j2, it auto-detects SLF4j and Java util logging in that order, and picks the first available one of those 3 in terms of the class path. It has a few implementation patterns that it follows, but those are not really so important. The most important part is streamlined setup. So if you're trying to use Log4j2, the only thing you have to do is put Log4j2 on your class path. Put Log4j core on your class path. Everything else just follows automatically. No manual excludes of the standard commons logging artifact from Spring Core anymore. No manual includes of any extra bridges. Simply use Spring, declare a dependency on Spring, put Log4j2 on your class path, it all works. Same for logback, same for any other SLF4j setup, and of course the same for the Java util logging fallback. If you want to use Java util logging, don't do anything, right? Don't put Log4j or SLF4j on your class path, and the default resolution is Java util logging. Yeah, I know we should have done that probably a little earlier, but it was a more convoluted situation before. We really wanted to streamline the setup for non-boot projects. In Spring Boot 2.0, you get that implicitly, but you didn't really notice so much of it before. But in particular, for non-boot setups, this is really a great help. So there's, yeah, that's essentially the commons logging bridge. There's a little more to it, some fanciness baked into the bridge implementation, but it works quite fine for all practical purposes today. All right, so a topic that has been showing up in the boot deep dive session today, the components indexer. So I'll quickly look at it from a Spring Framework perspective here. We have traditionally our component scan model, our component scan instructions, going into the class path, resolving certain base packages that you specify by name, or even the root packages, all the class path roots, according to class loader resolution. That's essentially going into the class path and saying like, into the class loader and saying like, get resource, give me all the roots of this package all across the class path. Then we dive through these directories that we find, and then we go into all the sub-packages and look into every single class artifact that we find there, and we look for certain indications called include filters, where we're trying to identify, for example, components by annotation type. And that's the components to manage in any given application context here. So the class path scanning algorithm is actually quite extensive. What we do when you say add component scan or a context component scan in XML here, what we do is actually quite elaborate. It's quite a search that we perform. In a standard environment, no JVM security manager, local file system, and no interception of I/O access, this is actually pretty efficient. We can search many jar files, many candidate class files. Even if you only have like 50 class files that you actually want to find, and you give us 5,000 class files to search, so we have to ignore almost everything that we find. Just 1% of the candidates actually match. It's still quite efficient. But what if there is a JVM security manager? What if you're actually bootstrapping from a network file system, from a remote file system? What if you're running on Google App Engine, where basically any I/O is super expensive? Then, and mostly then, the indexer model comes into the picture here. So instead of letting us search the class path every single time that your deployment unit starts up, you may provide a spring.components file in the meta-inf directory of your jars. If we find such spring.components files around, and we are being asked to perform a class path search for you, we translate basically that component scan specification. We actually we skip the class path search, the actual class path search, and resolve your search request against this component's index. This only works if you use the standard include filters. So if you want us to identify components by @component, @repository, @service, @controller, the standard annotation model. Spring Components is actually a pretty simple file format. You could almost handcraft it in a build process. But we do ship an annotation processor that goes through your project setup at build time, identifies annotated components at build time, and spits out the Spring Components file for inclusion in your jars as part of your build process. That's actually pretty convenient. It might not make much difference, but it's still quite convenient. And in larger setups or more demanding I/O environments, it may be a pretty essential improvement to just improve startup times. And then Google App Engine is a good example because not only is I/O slow on Google App Engine, it's also a highly dynamic, a highly elastic environment. So it might start up another instance of your service and shut it down again in 2 minutes, right? It might not live very long. So it might constantly start them up and take them down again. And in particular, in those elastic environments, it really matters if the same unchanged service unit is always being bootstrapped again and again and again. There are other ways of improving startup times for component scanning, of course, narrowing the base packages, or simply not using component scanning, enumerating the classes. It's actually quite straightforward. In scenarios, in microservice scenarios, that's totally straightforward. You can just enumerate the classes that you want us to register in some little startup piece of Java code. Yeah, so another variant, another option for the toolbox here, the component indexing model, completely transparent. No changes in your source code, the same component scan instructions, the plain inclusion of those index files in your jar files triggers their use at runtime. So it's in particular meant as an optimization for larger scale existing setups without changing the actual application setup at all. And as shown in the boot session today, this is actually quite useful also in a boot environment. So yet another topic, nullability. And nullability is, well, it actually came late. It even came post RC1. It was initially motivated by Kotlin, by the Kotlin compiler feature of, by Kotlin's rules in terms of interaction with Java APIs. Java APIs traditionally don't indicate their nullability. They don't formally indicate whether incoming parameters are supposed to be null, whether the return values of any Java method returning a non-void result, whether that return value can be null. And in particular, the latter part is really important. Really important for Kotlin. So if you're calling a Java API and you'd like to assign the outcome to a non-null type declaration in Kotlin, the Kotlin compiler is basically not going to accept it unless there's a clear indication that the outcome of the Java method call can never be null. And there are several variants of expressing this, but the recommended one are simply nullability annotations, at nullable and at non-null annotations on those artifacts. The Kotlin compiler is simply going to say, like, OK, if it says non-null here, I assume that's actually true. It can't verify, of course, that it's actually true, but basically the formal declaration that you do not ever intend to return null from this particular method is good enough for the Kotlin compiler to accept such an assignment. So that was the original motivation. But it turned out that this is actually a quite useful exercise for the entire code base on our end and for even using Spring APIs from Java code. So what we did was really extensive. We went through our entire code base several times. There were several commits with about 1,000 files modified in every one of those commits. So we started introducing nullability annotations for the method level initially. Then we went down to the field level. We started using the IntelliJ IDEA features for nullability validation. So identifying spots in the code flow where you make assumptions about the nullability state of certain fields that are not actually true. This is super useful. It even understands volatile variables, so that basically where a reference could turn null underneath the covers, you shouldn't make assumptions in sequential steps about nullability of volatile variables. Take a local copy. And if that initially wasn't null, then it won't be null afterwards either, right? So really useful validations that we are using internally to identify corner cases in our own code base, in the code flow in our own code base. It also shines through to applications. So from Java application code, calling into Spring APIs now, you could turn on those validations in IDEA yourself, right? So if you're calling bean factory get bean, there's a clear nullability rule to it now. That it's in a regular case, it's a non-null result in Spring Framework 5 now. And JDBC template, whatever else, right? So even for Java code, you could actually start using those validations, and through our layer of declarations here in the Spring APIs, you can also make clean assumptions when calling our APIs from Java code. The IDE can make clean assumptions. Yourself, your mental model of what you're interacting with here, can also make clean assumptions. So it's also a formal declaration. If you find out whether this can be null or is meant to be null, instead of going into the Java doc and hoping that it's up to date, you can also look at the formal nullable declarations. They have to be up to date because we are actually using IDE level introspections that will immediately indicate a mismatch. So it's a really fine effort overall, but it was actually quite some effort. Just one more detail before we move on. We actually chose to go with a non-null by default declaration. So if you look at our code, if you, for any reason, dive into our code here, you'll find out that it only has nullable annotations in most places, because most of our packages are non-null API by default and non-null fields by default. So the actual classes only annotate exceptions to that rule. It's non-null by default. Only artifacts that can actually be null have an explicit nullable annotation. If there's no nullable annotation on it, it's meant to never be null by default. This is actually quite nice because it doesn't clutter the code base so much with non-null annotations everywhere. All right. Somewhat related, because it's also a little Kotlin inspired, but turned into a general refinement, is data class binding. In the Spring Framework, data binding model can be triggered from several places, but typically from request parameters onto an object that you're passing into a Spring MVC handler method, for example. Data binding along those lines, any use of literally the data binder class in Spring, is traditionally bean property based. So those objects would have setters and getters. There was a mode of field level binding. So we had a couple of years back the request to support direct field binding. So we do allow for that, but basically still it's a mutable object. You're either calling the setters or we are populating the fields directly. That was basically data binding, web data binding, or also data binding from message formats and others. In Spring Framework 5.0, this is a little smarter now, following actually a pattern that also goes through the core container. In terms of making assumptions about constructor signatures, we also look at the constructor signatures here now. If we are about to bind to a data class, or we are supposed to pass such a binding result object into a handler method of yours, and there's no default constructor, then quite clearly this is not a traditional Java bean. Previously, we would have failed. We would have complained there is no default constructor, please declare one, right? Now we are a little smarter. We actually branch into a different mode of binding. If there's a single, unique, non-default constructor taking a number of arguments, then we assume that this is actually a data class. Data class as in a Kotlin data class or a Lombok data class as a kind of pattern, an immutable class populated through the constructor. It might or might not have getter methods to access those fields. Doesn't really matter for that field of use, but in general it would have getters. But it's an immutable data class populated through the constructor. We introspect this unique data class constructor. We take a look at the parameter names. The parameter names are actually significant here, so they have to be retained in the bytecode. Please do compile your classes with dash parameters in Java 8, or at least with dash debug, which we generally can also use to resolve parameter names. But dash parameters is the first class flag in Java C in Java 8. So the parameter names are significant, and we resolve the incoming property values, like web request parameters. Again, we match them against the constructor signature and simply resolve all the constructor arguments, then call the constructor for you, pass the object in. This rather simple mechanism is surprisingly useful. In particular, since Kotlin actually has a data class model where you can literally say data class, like person, right, and then just then just declare a sort of constructor-like signature, and that immediately turns into a full-fledged data class with the fields generated, the getters basically generated, right? It's a very, very concise signature and a very common pattern. It turns out that Lombok has a very similar pattern in its add-data model. Basically, add data, add all args constructor, and then a declaration of fields within a Java class turns into a very similar outcome. And you can handcraft it in Java, right? It's just a pattern. Create a Java class with a single constructor, taking all the fields, proper parameter names, assign them to final fields, declare some getters, declare equals hashcode toString, and you've basically got the same pattern handcrafted in Java. And our mechanism here, the data class binding mechanism, works with any implementation of that pattern. So there's not even specific support here for like Lombok, or not even particularly specific support for Kotlin. It's simply a general purpose pattern implemented in the data binder now. Side note, there is a little bit of special Kotlin support in identifying what Kotlin calls a primary constructor. But this is not specific to data binding. We're using the same mechanism in other places of the framework. So Kotlin has a little bit of a special role in us using the Kotlin lookup API for primary constructors, allowing for an arrangement where there would be several constructors, but one is primary. We accept that as well. So it's either a single constructor, that's the common case, or what we call a clearly indicated primary constructor, which is in particular relevant in Kotlin. All right, 3 slightly minor, but still nice enough refinements here. There's a Spring Framework 4.3 feature called Object Provider. So if you declare an injection point at autowired, instead of saying at autowired mybean, you can always say at autowired object provider of mybean. Object provider is essentially a little lookup API with a get object method and several other accessor methods, get methods, allowing you to be a little bit smarter in when you obtain an object to the actual target object, right? So at autowired mybean would immediately inject the mybean instance into your class at the point of declaration. Whereas object provider of mybean can lazily resolve an object. You can always freshly resolve a prototype instance. And you can request an object under certain conditions, like give me the object if actually available, null otherwise. Give me the object if it's unique, and null otherwise. So if there's only one of them. If there are several, I don't care. I only want to have it if there's one clearly identifiable single object of that type in the application context. The traditional get if available and get if unique methods are nullable. Now they're actually explicitly nullable, but they were already returning null before if the object couldn't be found. In addition to actually annotating them with that nullable now, we overloaded new variants, which are pretty useful. We have a get if available with a default supplier. So if available, I want the target object from the application context. If not available, here's a supplier, usually an inline lambda expression or a Java 8 method reference, producing the default instance that I'm going to use from here on, which allows this get if available supplier signature to be non-null, right? It always returns a concrete instance. The same for get if unique, of course. And we also have if available variants with a consumer, which is a little bit functional here, right? Functional style. So you could say object provider, if available, if your target object in the application context is actually available, I'm going to consume it with this lambda expression here. So there's nothing returned from those methods. They're basically triggering a callback if the object is actually available. This is for slightly advanced injection scenarios. This is surprisingly useful. And if you go into Spring Boot 2.0, some of the implementations, some of the conditions, some of the setup logic there, you'll find use of these facilities already in the Spring Boot 2.0 milestones. All right. Another area of refinement, the resource abstraction. Plenty of stuff being refined there in the internals. Some new methods introduced in the resource abstraction itself, like basically optimizations. Instead of trying get file and getting an I/O exception back, you can also check whether it actually is a file in the file system that you can open as a file before. We improved some of the rules for when you would get a writable resource back. So generally, file references in the local file system are now actually returning a writable file URL resource that you can actually reliably downcast to a writable resource. So there are a few nice refinements for consistent usage of the resource abstraction. More importantly, we also upgraded everything we can to the NIO2 API. So the standard implementations, not only of the file system resource, but also of, for example, file copy utils, all the implementations use the NIO2 API now, introduced in JDK 7, basically using the files factory for streams, not using file input stream and file output stream anymore, which has some nice benefits, not only in terms of performance, but also in terms of garbage generated during reading and writing. That has to be cleaned up by the garbage collector afterwards. So the use of NIO2 is something obvious. We have a baseline of Java 8 now. We can rely on NIO2 being present. We're really embracing it. If you'd also like to embrace it, there are new methods on, for example, resource, giving you an NIO2 channel for reading, or on writable resource, giving you an NIO channel for writing. So it's also a more natural interaction with other NIO2-based code that you might have, or that you might call from another library or another framework. So last but not least, in the task executor abstraction and task scheduler, we introduced a couple of really convenient overloads. Maybe not too big a deal, but if you're heavily interacting with asynchronous tasks, this is also surprisingly useful. So not only are there overloads for like Java time instant and Java time duration, instead of specifying like a Java util date and that sort of stuff when scheduling by rate or by delay, there are also there's a new mechanism for monitoring the tasks that are currently scheduled. So this scheduled task holder mechanism is actually quite useful. You can ask the context for all scheduled task holders, which will basically give you a complete representation of all the currently scheduled asynchronous tasks sourced from anywhere, whether from @schedule, from programmatic scheduling, you're going to see a complete representation. And the scheduled task endpoint in Spring Boot 2 makes use of this, of course, but it's a programmatic facility at any point in a custom monitoring solution or a custom endpoint that you're designing for those purposes. You could also introspect those tasks. You could see them. You could even go as far as, well, making decisions about canceling them under certain conditions, whatever. Right? It's a programmatic facility of interacting with a declaratively scheduled tasks in particular. All right, and there's the completable future integration, which can be pretty useful. We have our own abstractions for historic reasons, and also for some simplification reasons in our scheduling abstraction, and interaction with existing completable future-based code is quite important in its own right. So you'll also find that in a convenient programmatic fashion now. All right, so that's really all I had for you in this brief little selection of topics not usually covered, but still being quite useful in Spring Framework 5. Thanks for your attention. There's a party out there.